Hey everyone, so what we saw today in the demonstrations and in class is that the reason that there is gravity is due to warping of space and time. So when you put a mass in a gravitational field, what it does is it warps the space and time around it. And then other objects will respond to the warp in that gravity field and either get pulled towards it, or if they're zipping by very quickly, they'll move around it. And one thing that we did see as we had those little marbles orbiting the mass in the center is that when they went around the central mass, they did not travel in nice circular orbits. They traveled in more egg-shaped or elliptical orbits. Now we did talk about the orbits decaying, and the decay is all due to the friction of the balls rolling around the material. But in space there is no friction, so it's going to just continue in its tangential motion. However, it's not going to travel in perfect circles. It's going to travel in elliptical paths, and that was the first thing that Johannes Kepler found out when he was observing planetary motion. So he came up with 3 laws based on all the measurements that he got from his master. He looked at all the paths of the planets and found out that they travel in ellipses, meaning that sometimes during the year the planet is close to the sun, and at other times of the year the planet is far away from the sun. There are 2 terms that astronomers use to talk about those 2 locations. You can see it says RP down here, or RA. The RP means radius when you are at perihelion, and RA is the radius when you are at aphelion. The way I remember that is just A for far away and P for pretty close. So you've got those 2 ways to remember that objects move in ellipses. So you think, okay, we have that. What does that matter? What does that mean? So what? They're not circular paths. So Newton's second law says that any satellite, and a planet is really just a satellite of the sun, where the moon is the satellite of Earth, will sweep out equal areas in equal amounts of time. So if you look at that triangle, that thin triangle for the planet, if that takes 1 month for the planet to travel that little triangle, when you get close to the sun, that bigger triangle takes the same 1 month time. However, the 2 areas are exactly equal. And so I have a little thing in parentheses there that says that we're really just conserving angular momentum. So let's think about this in terms of angular momentum conservation. The planet is a certain radius away when it's at this part in its orbit, and it's moving with a straight line. All objects want to move in a straight line. They don't want to follow circular or elliptical paths. So that means we have angular momentum in r cross p. So rmv for the planet way out here. We'll call this our aphelion distance. Now when we look at our perihelion distance is much closer. But again, the planet doesn't want to go anywhere but in a straight path. So it still has angular momentum in r, m, v at this location. Now if you look at that, we want to conserve the momentum before and after, because we always want to conserve momentum. Well, the thing that's the same on both sides is the mass. So really, the size of the planet really doesn't matter. It all matters with how fast you are moving. So in the first part, the radius is really large, and the planet will be moving with some tangential velocity. When the planet sweeps in close to the star, the radius decreases. And we know from angular momentum, when you decrease the radius and you decrease that moment, you're going to increase your speed. Just like when I was riding on the table or on the chair and pulling my arms in or opening my arms up. When the planet's far away, the arms are wide open and the planet moves slowly. When it pulls inwards, it decreases its radius and increases its speed to conserve its angular momentum. So that was what he means by equal area and equal times. Just that planets speed up when they're close to the sun and they go slower when they're far away from the sun. For a question, when is it summertime on Earth and when is it wintertime on Earth? Is it when the sun is at perihelion or aphelion? And that question can be a trick question, because for when I say summer and winter, I'm talking about summer and winter in the northern hemisphere. whenever we talk about summer and winter in the southern hemisphere, they're opposite our seasons because of our tilt. So for us in the northern hemisphere, we have winter when we are closest to the sun, and we have summer when we are furthest from the sun. And again, how elliptical you are all depends on the eccentricity of your orbit. So if you look to that planetary fact sheet I gave you, it'll tell you how eccentric it is. The closer it is to 1, the closer the planet orbits in a perfect circle. The further from 1.0 and the closer to 0 is how elliptical that object gets. So looking at those masses rolling around the central mass there, you see a lot of them heading way out far away from the central mass, but they're all being pulled back inwards, and when they get close to the mass, they're decreasing the moment of inertia and they increase their velocity. This is exactly what comets do when they zip around the sun. They have very, very elliptical orbits, so they get very close to the sun, heat up, and start to melt, or they get far away from the sun and they slow down and cool off. So then that brings us to Kepler's third law. And Kepler's third law says that the time period for a satellite to orbit squared is equal to some constant multiplied by the radius of orbit cubed. And he got that without even knowing what that constant was. He timed planets, and timing the planets, he was able to actually place the planets in our solar system by knowing how long it takes them to return to the same place in the sky. So for one full orbit, one full time period, let's test this out for Earth. Time period for Earth to go around once is 1. Why do we call it 1 year? Because we're the only ones here in the solar system. No one's going to argue with us and tell us that it's more than 1 year for us to go around the sun. Well, how far away are we from the sun? There is an exact 93 million mile answer, but astronomers like to say we are technically 1 AU away from the sun, which is 1 astronomical unit. Again, why do we call it 1? Because no one's going to argue with us. So when we do this, we do 1 year squared and 1 AU cubed. Your constant is 1 for Earth. So knowing what the constant was in terms of just using 1 year and 1 AU, we can then time another planet. We time another planet, and that planet ends up with a time period of a half a year, half an Earth year. The question would be, well, how far away is that planet? So half an Earth year means it orbits quicker. So based on the calculation here, let's do that and solve for radius. So it's 0.5 squared over the constant, and you take the cube root of that, and when you do that, you get, so 0.623 AU is the time, or is the distance of orbit for a planet going around our sun that would orbit in about a half a year, just based on Kepler's third law. Time squared equals a constant r cubed. Now this only works, that constant is only 1 if you use the units year and a radius of astronomical units. If we use seconds and meters, that constant does not equal 1, and where the heck did he get that equation anyway? So let's show where this derivation came from. So the way you want to think of this derivation is you want to think about the object that is orbiting another one. So say the moon going around us, or any satellite orbiting any other object. So the moons of Mars or the moons of Jupiter can all be considered satellites, and if we assume that they are moving almost in circular orbits, what we can say is that there's a centripetal force causing them to go in a circle. So gravity becomes our centripetal force. So we know that the gravitational equation here is big G, mass 1, mass 2, all over distance squared. And for centripetal force, we know that to solve for centripetal force, you take your mass times acceleration, which is v squared over r. So the question is, what masses are we talking about and what radius are we talking about? Well, we always measure the force of gravity between the center of one object to the center of the other. So you need to know how far you are off the planet plus the radius of that planet to give you your full r value. And if you look on both sides of the equation, I have an r on the bottom and an r squared on the bottom, so I can actually knock out one of those radiuses. Alright, let's talk about the masses. We've got two masses in our gravity formula. One is the mass of the planet, and one is the mass of the satellite. Over here, in the centripetal force, I have mass times v squared over r. Which mass is that? Well, this is the mass that is centripetally accelerating, which ends up being the satellite. So we can actually eliminate the mass of the satellite. So that means it doesn't matter how big of a satellite you have, as long as we get it to go this speed, the object will orbit. So when we solve for velocity here, you get the velocity to be g(m) over r, square root. So what we've given ourselves here is a formula for orbital velocity. If you want to know how fast you need to go to orbit a planet, you need to know the gravitation constant, you need to know the mass of that planet, and you need to know the radius of the orbit you're interested in. Not the radius of the planet, that would be orbiting at ground level. So that's how you get orbital speed. And what does it mean to orbit? Well, what Newton thought of, and he had an idea of putting a cannon on top of a mountain. And he said, what if I had a mountain with a cannon on top and I fired a projectile horizontally? Well, we know from projectiles that projectile would just head out with a nice constant horizontal speed, and the vertical speed would bring it to the ground because of the force of gravity keeping you on the planet. So what if I packed more gunpowder in there? Well, we'd see the same thing, except we get a much larger range. And the nice thing is it would be the same time for it to fall to the ground. Let's try this a third time. Third time with more gunpowder, even further. And this would be true if we lived on a flat planet forever. But eventually the Earth does start to curve. If you go far enough, the Earth isn't perfectly flat forever. So if you fire with just the right amount of gunpowder, you fall, but you never hit the ground. And that's all orbit is. That's all the satellites are doing, or the space station, when they go up and around and over your head. They're moving so fast that they are falling, and every second they fall around the curve of the Earth. So if you had that cannon and you fired fast enough, the object would just continue to orbit at whatever speed you give it, and it would never lose that speed if there was no frictional forces on you. Orbital speed for Earth, if you punch in your numbers, I know it's on your fact sheet, but I like the miles per second, so you'd have to put your distance in miles and your mass in slugs, which is a really weird unit, and change the g constant, but solve for it in kilometers per second and convert, and you should get around 5 miles per second, which is pretty fast. A mile on the track is 4 laps, so we're talking 20 laps in 1 second. So every single second of orbit, you'd be traveling 20 laps around a track if you can move at orbital speed. That's really fast. And just to bring astronauts back, all they do is decrease the speed. You decrease the speed, and you eventually do crash into the ground. If you want to increase that orbit, just increase the speed, and you get further and further radiuses. But that's not what Kepler's third law was trying to get us. It wasn't trying to get us orbital speed. What it was trying to get us was the t squared r cubed relationship. So let's look at orbital speed. For us to orbit, we would travel a distance around the circle, which would be our circumference, divided by the time it takes us to do that. That's just old circular motion velocity. We're going to put that in for v here and make sure you square everything. So when you square the straight line tangential velocity, you get 4 pi squared r squared over t squared equals the big G constant, the mass of the object you are orbiting, and r, which again is the distance of your orbit. So we want to combine this and find t squared and r cubed. So I'm going to move r over to this side, and I'll get an r cubed, and I'm going to move t squared over here. So I'm almost there. I almost have the constant that Kepler came up with the t squared r cubed relationship. I've got t squared on one side and r cubed on the other. So everything else should be my constant, and there you go. There is Kepler's constant. He didn't know all these things, but he used the time and orbital distance ratios to give him the positions of all the planets, but now we can have an exact time and an exact radius for each of our setups. So t squared is our time to orbit, and r is our radius. So the constant in there is 4 pi squared over gm. Remember that g is the gravitation constant, and m is the mass of the thing that you are orbiting. So if you put in the mass of the sun here, what it'll tell you is that if you pick any orbital distance, r, from the sun, it'll tell you exactly how long it'll take you to orbit. If you put in the Earth as your mass there, it'll tell you where to specifically place an object and give you an exact time for that object to orbit. So this is exactly how they know that the space station takes about 90 minutes to make it back around to the same spot. So when you go outside and watch the space station fly over you, remember it isn't free fall, but they've already calculated that the distance it needs to be at gives it a 90-minute orbital time period. If you want to track things like the International Space Station, there's plenty of links. Heavens Above, NASA, there's many different websites that will tell you exactly when the space station is orbiting, where it is at this exact moment, so that you can track it and watch it go through its free fall around the Earth.